just to review some of the major sort of formulas that we use in acid-base chemistry to do calculations. Obviously, we have our Kw, which is concentration of H plus times concentration OH minus, which equals 1 times 10 to the minus 14. Again, we can use Kw really to figure out either the H plus concentration, which is really the acid part of the solution, or the OH minus concentration, which is obviously the base part of the solution. And obviously we would need just one of those given to us, or have one of those values. And obviously just comparing the H plus to the OH minus concentration will tell you whether or not the solution is acidic, basic, or neutral. Obviously, if the H plus is larger, that means it is acidic. If the H plus is smaller, which means the OH minus is larger, then it would be basic. And obviously, if they were equal to each other, we would be neutral. So that 1 times 10 to the minus 14 is pretty much a number you always have available to you. And regardless of which one you are calculating, it is pretty much the same calculation, 1 times 10 to the minus 14 divided by the other concentration. We also talked about the pH scale, and obviously it runs from 0 to 14, 7 being neutral. The pH is equal to minus the log of the H plus concentration. A similar sort of scale measures the OH minus concentration, which is minus the log of the OH minus concentration. And those two sort of values are really useful because there's a nice relationship between them, that if you take the pH plus the POH, it will equal 14. And again, this gives you a little bit of options in terms of how to sort of solve some problems. It will allow you maybe not to have to use Kw. So for example, as we saw, if you have the OH minus concentration given to you, you could simply calculate the POH first and then just subtract 14 and you have your pH. So it gives you a little bit of flexibility there. The other thing we talked about as well is if you do have the pH from that value directly, you could get the H plus concentration, which is the inverse log of the minus pH. And again, on most people's calculators, when you hit that button, or two buttons usually, it will put a 10 and a caret up usually, and then you want to make it negative with the POH. And again, usually like the second or shift button and the log button is really the two buttons there that you want to kind of hit to do that. We also could do the same thing with our POH. If we have the POH given to us, once again, we could directly get the OH minus concentration from it by doing pretty much the identical calculation here. The OH minus would equal the inverse log of the minus POH. And once again, like a 10 and a caret to the minus POH. So these do give you a variety of ways to sort of solve some of these problems. And obviously, if you have the pH, you could get either get the H plus concentration, and you could also get the POH and get the OH minus concentration. So again, you may not have to use Kw. But as we saw in a couple of examples, you could absolutely use Kw. It also sort of gets you the same spot. Again, you might have a slightly different answer if you did a lot of rounding or something like that, but it should be fairly close no matter sort of which way you go. Other important things we talked about, obviously, is in this chapter, H plus and OH minus, they run opposite of each other. So as one goes up, the other goes down, and it's sort of inverse relationship. And we also talked about, obviously, the pH scale runs from 0 to 7 to 14. And obviously less than 7 is acidic, above 7 is basic, and 7 there is neutral. Remember that you should always look at the pH value to determine whether or not it's acidic, basic, or neutral, because that is usually the scale everybody has in their head. You do not want to go off of the POH value because it does run opposite in terms of numbers. So again, if you have a large POH, you have a small pH, and vice versa. So they are opposite sort of values of each other. And always give only one answer for that question: acidic, basic, or neutral. Not all three, or all 2 or 3 of those sort of answers. Any questions on any of that stuff we talked about, I think, last time? Okay. So let's talk about what happens when we're trying to find the pH of a strong acid. So something like hydrochloric acid, which is a strong acid. Remember, we made a list sort of some strong acids. Once again, hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid. So again, this is sort of a list of strong acids. Because they are strong acids, as we've talked about, they are strong electrolytes, which means when they are in solution, they will once again 100% break apart into H plus and Cl minus in the case of hydrochloric acid. And the important thing in terms of pH really is the H plus concentration. And that's because, again, pH is equal to minus the log of the H plus concentration. So in a situation like this, because we have 100% everybody on the right-hand side of the arrow there, pretty much if we know the concentration of this guy, it will be the same concentration for the H plus concentration. And that is because it is a 1-to-1 relationship in terms of stoichiometry on one side to the other. So in a monoprotic acid where there's only one hydrogen to give, and if it is a strong acid, if you know the concentration of the whole acid, that is also going to be the concentration of the H plus concentration. So really that would be all we needed to go into our pH equation. So if we had something like 0.1 molar HCl, when again this breaks apart, as we see above, if this is 0.1 molar, once again, it is a 1-to-1 relationship between this, which means the concentration will also be 0.1 molar for the H plus in the solution, which means once again, that is all we need. So we could go into our pH minus the log of 0.1. That will get us a pH of 1, I believe. And I'll give pH of 1.00, which is obviously acidic, I would assume, as well. So sometimes in our in problems and stuff, you may not just be given just a generic H plus or H3O plus as the concentration. You may be given an acid, and probably it should be one of those guys up there on top. For our purposes here, it will most likely be a strong acid, because if it is a weak acid, it's a much longer calculation to figure out the pH, which you'll do in Chem 1B. But so you could probably be pretty safe if they actually do give you a formula of an acid or even a base, by the way. It will be a strong acid or a strong base in this class, and you can basically figure out the H plus concentration. Also, the other thing we also talked about as well is sort of sig figs, right? So a reminder that this guy's got two significant figures, which correlates to, again, not two significant figures, but two decimal places in the pH value. So again, that is why we take it to 1.00. You could also apply this same sort of thing to a strong base, except obviously if you had a strong base like sodium hydroxide, it would break apart into a sodium ion and a hydroxide ion. Now, in this particular case, it would actually be the hydroxide ion that would be important, obviously, for pH. And once again, here, this would be a 1-to-1 relationship, which means that we could actually calculate the POH from that. And once we have the POH, we could get the pH by subtracting the 14. So you could also do this as well, again, for something that's a strong base. You just got to do the POH first and then get yourself basically to the pH. Any questions on that there? All right, so why don't you try one here, calculate the pH of 0.025 molar perchloric acid. While you're at it, also calculate the pH of 0.025 molar calcium hydroxide. Strong acid and a strong base there. Number one there is calculate the pH of 0.025 molar perchloric acid. Again, that's one of those strong acids that was on our list. So what we know about perchloric acid is it should, when it's in solution, obviously 100% break apart into H plus and really perchlorate. It is really the H plus concentration that we need for the pH. And when we look at this is 0.025 molar. It is a 1-to-1 relationship between the whole thing and the H plus concentration, which means the H plus concentration would be also 0.025 molar. So would the perchlorate, although we don't really need it in this particular case. That is really what we need. So we can then go into our pH, which would be minus the log of 0.025. That is going to give us a pH here of, looks like a 1.60, which is acidic, and this is an acid, so that's all good, right? So again, have you got a pH of 20 here or 10? They did something really wrong. Any questions on that one there? So when we look at the next one, which is calcium hydroxide, so since it's got hydroxide in it, it is a base, and probably again for our class, you could safely assume that it's a strong base. It is, if you remember, if you kind of start at lithium on the periodic table, come down to potassium, go over and come down. Any of those guys there from group 1 and group 2 that has hydroxide in it are typically a strong base. So because this is a strong base, it will also 100% break apart in solution. And when it does, we will get a calcium ion, and we will get actually 2 hydroxide ions here. Once again, in this case, because it's a base, it is the OH minus that's important. It's not going to allow us to get to the pH directly, but we can get to the POH and then obviously to the pH value. In this case, the calcium hydroxide concentration was also 0.025. It is a 1-to-2 relationship here between the whole thing and hydroxide, which means you need to adjust the concentration by multiplying by 2 to get the correct concentration there. So you would want to take 0.025 times it by 2, and that gives you 0.050 molar. That would be the correct concentration for hydroxide in this case. That would allow you to, like I said, go into the POH in this case, which are 0.5. That is going to get you a pH of 1.30, which a POH of 1.30, which then you can get the pH by subtracting 14 from that. And that gets you like a 1270 here. So a couple of things, if for some reason you thought the 1.3 was the pH, that should not make sense to you, obviously, since this is a base. And obviously 12.7 is a basic pH, which does make sense. So, you know, if it happens again, not to break apart into a 1-to-1 relationship, you do need to adjust, obviously, the concentration by the coefficient, basically. As we talked about when we did solutions, that's sort of the quick way to do it, is just if it breaks apart into a 1-to-2, times it by 2, 1-to-3, times it by 3, and so forth, obviously. Any questions on either of those? Any questions on calculating pH, POH, H plus, anything? Okay. So the last thing that we're going to talk about in this chapter here are buffers, and sort of what buffers are, and again, how they really work. And I think we might have talked a little bit about it when we did the lab, but just to officially, once again, go over it here. So a buffer, there it is. A buffer is a solution that will be able to resist changes in the pH, even if you add some acid or base to it. Again, we might have talked about a very sort of wrong misconception that a lot of people have about buffers, is that it is a neutral solution. And it can be neutral. And as we talked about, I think in lab as well, you can really make a buffer at any pH you want. So you can make an acidic buffer, you can make a basic buffer, and obviously you can make a neutral buffer as well. But basically the point of a buffer is the fact that when you make it, whatever pH it sort of starts at, it will basically be able to maintain that pH And if you sort of make it all correctly, it should be able to maintain it over a good period of time there as well, even when you add acid or base to it. So what you should have saw was obviously in that experiment, the water one, you just added like a drop or two, and then you saw a pretty good jump in pH, which water is not a buffer. When you added it to the buffer, you were counting a lot of drops, I think, yes. And, so, over 100 or however many, just to get it to move a little bit along the way. What a buffer is made out of is really a combination of one of two combinations, I guess. It can be a weak acid and the conjugate base, and that is also sometimes referred to as the salt of the conjugate base. Or you can make a buffer out of a weak base and the conjugate acid, or the salt of its conjugate acid. So it's really important, and that's really why a buffer, as we'll talk about here, is able to really function and work well, is because they are made out of a weak acid or a weak base. You cannot make a buffer out of a strong acid or strong base, where the strong acid, strong base, you're going to call a buffer. It will not work, right? The reason for that is a weak acid or a weak base basically is a weak electrolyte, which means if we took something like hydrofluoric acid, which is a weak acid, it would break apart into H plus and F minus. Where if we were to make a buffer out of this guy, we would make a buffer out of HF and maybe something like NaF, which is sodium fluoride. And when we do that, the sodium is really the salt part of it. That's why it's called the salt of its conjugate base, because it has a sodium there. The really active part of the buffer is these two guys. So when we dump in some hydrofluoric acid, it's going to set up this equilibrium that's going to keep both of those guys basically in solution at the same time. So it allows both of those guys to remain in solution at the same time. We help it along when we make a buffer by adding some sodium fluoride, because that is a source of F minus. So we get a nice good amount of both of those guys that are able to basically stay in that solution at once. And what that essentially does is when you make a buffer like this, is you basically have an acid part to the buffer and you have a base part to the buffer. And that's really important for how a buffer functions, is that both of those parts of the buffer are in the solution basically to begin with. And when you add acid or base to it, that's why it's able to basically take care of it and keep the pH from going crazy. So let's take a look at sort of, what's going on in a buffer and a non-buffer situation, so we can understand sort of how a buffer like this can function. So obviously, if we add it to a non-buffer like water, and if we added a strong acid like hydrochloric acid to water, so if we added this to water, what we were just talking about, it would 100% break apart in that water into H plus and Cl minus, right? So again, 100%, this is what we would have in water. And that's really important, because if we think about the pH equation, basically what we did is we just generated a lot of H plus really quickly in that solution. And as the concentration of H plus increases, the pH starts to decrease, it goes down. And this is why when you hit the HCl, the water with the HCl, a drop or two, you saw it jump pretty quickly in terms of pH, because you rose the H plus concentration. And by default, the OH minus concentration also came down, and the pH came down with it. So because it's not a buffer, the water basically just sits there and can't handle anything that allows all that H plus to be in that solution. And it really is free H plus that affects the pH of a solution, hence the pH equation here. If we took a strong base and added it to a non-buffer like water, what would happen is, again, just like we just talked about as well, because it's a strong base, it will break itself apart 100% into both of these guys. And just like above, at this point, we just generated a lot of OH minus free in the solution floating around. And we would see that the OH minus concentration would jump up. The result of that is that the H plus concentration would go down, and we would see that the pH would start to jump, again, go higher in this case, because there's now a lot more free OH minus floating around in that solution. Once again, in this case, water really can't handle the addition of that more OH minus. So it just sits there, it floats around, and it affects the pH as well. And again, that's why if you hit your water with some sodium hydroxide, you also should just all it kind of jump up pretty high with not a lot of drops, for example, being added to it. So in a non-buffer situation here, when we look at both of these guys, when we added the HCl, we just generated a lot of H plus in that solution, going to make the pH pretty much drop a lot. When we added the sodium hydroxide to our non-buffer, we added a lot of free OH minus floating around that solution, which is going to make the pH kind of go up and you get this big sort of jump in pH. So now if we take these same two things and add it to a buffer situation, some different reactions sort of occur when we do that. So let's take a look at what happens when we do add these guys to a buffer. So if we added it to a buffer, and we could even use the one we just talked about there, HF and NAF. By the way, other sort of buffers, common buffers, the one you guys did in class, which is like acetic acid and sodium acetate. These are some common buffers. Also, NH3 and NH4 plus is a common buffer. That is a weak base and a conjugate acid. So those are some common buffers that we see. So if we take the same HCl and we added it to our buffer, and we'll look at this guy right here, this buffer. This buffer has, again, two parts to it. Both of these guys are in solution to begin with. It has an acid part and it has a base part. So when I add my hydrochloric acid here to this buffer, would the acid react with the acid part or the base part of this buffer? Should react with the base part, right? So what will happen is, in this case, the hydrochloric acid and the sodium fluoride will come together. It'll do a double displacement reaction. It will produce HF. Basically, these two guys switch. And we will produce some sodium chloride in this particular case. So what we see here on the product side is a couple of things that have been formed. First off, we have formed hydrofluoric acid, which was in the buffer to begin with. So we basically formed what was there to start with. So what we had in there originally was these two guys floating around. We also produced this sodium chloride, which basically came from a strong acid and a strong base. This is a neutral salt. It is relatively weak, won't do much. So we produced something that was there before, which won't mess up the pH, but more importantly, as we might have talked about during lab time, it's actually what we don't see here. So we do not see any free H plus that would normally come from this acid. And because we don't see any free H plus like we did in the previous one, right, when we added to water, we saw a lot of H plus really quickly. What we end up with is the concentration of H plus stays relatively constant. And if the concentration of H plus stays relatively constant, that means the pH should also remain relatively constant. So as you saw when you added, for example, your hydrochloric acid to your buffer, it took a lot of drops to even get it to move anywhere in terms of pH. That's because it has both a part and a base part in it to begin with. So when you add the acid here, it's able to really tie up that H plus that normally would be free in the solution. And because we keep the H plus concentration going up, we keep it relatively constant, and it keeps the pH relatively constant. I say relatively constant because, frankly, if you threw a pH meter in there and you really were following the pH, you would see the pH move a little bit. So, like, again, if it was like a pH of 5, it would maybe drop to like a 4.9-ish or something like that. But it wouldn't go from like a pH of 5 all the way down to a pH of 1. If you added it, it will have a very small sort of decrease in the pH in this example. And you won't see the very big swings in pH that you do in a non-buffer situation. Any questions on that there? Now, if we did the same thing, but we added our sodium hydroxide to this buffer, so we'll look at the same buffer here. So we were using our HF and our sodium fluoride, which again is our acid part of our buffer, and our base part here. By the way, these are a buffer because it is a weak acid and its conjugate base, which means the Bronsted-Lowry definition is it is 1 H plus difference between these two guys. This is really the functioning part of the buffer. There is this, again, the sodium is just hanging out to balance out the charge, not doing much. So if we add our sodium hydroxide to this, which obviously is a base, we would expect it to react with the acid part of the buffer that's in there. And we would get our HF, and we would get an acid-base reaction here that would occur, which means we would make water, and we would make some NaF in this case. Again, double displacement move right there. Once again, we made water, which should not mess up the pH. We also made sodium fluoride, which was part of the buffer to begin with. And by the way, that is always what happens when you have a buffer and you add acid to it or base to it. It basically will use up some of the buffer, but make the other part. So we kind of make some of the part of the buffer as we react with it. So in this case, we're going to use up a little bit of the H plus, but we're going to make some of the NaF. And that's really how a buffer is able to function over a long period of time. You kind of regenerate part of the buffer as you're reacting it with it. But once again, it is what we don't see here that's really of importance, and that is that we do not see any free OH minus formed. And once again, because the OH minus concentration stays relatively constant, the H plus concentration stays relatively constant as well, because they are tied to each other. Remember, one goes up, one goes down. So if you keep the OH minus constant, the H plus will not go anywhere, and that will once again keep our pH relatively constant as well. And once again, if you were following it with a pH meter, you would see a slight upwards trend in this case of pH, but you would not see it again if it started at a pH of 5, jump all the way to like a pH of 12 or anything like that. If you made everything correctly, it should be able to resist the change. So ultimately, what a buffer is able to do is it's able to prevent the formation of free H plus when you add an acid, and that's going to keep the pH relatively constant. And it's going to prevent the formation of free OH minus when you add a base, and that's also going to keep the pH relatively constant. And that is ultimately how a buffer works, is by keeping the concentration of H plus or OH minus relatively constant when you add more acid or base to it. Any questions on how a buffer sort of functions? Now, when we make a buffer, sometimes, you always want to, it's really important to make a buffer with the correct molarity and concentration and appropriate for what you're going to use it for. So a lot of times when you do make a buffer, they want to start with kind of equal amounts of the acid and base part of the buffer. And that's usually a really good way to kind of make a buffer. So, when we start, for example, and we make a buffer, this is our buffer, if you will. And again, the acid part of the buffer, the base part of the buffer. When we take this buffer, and again, when we add some acid to it, it will use up some of the base, right? It's going to basically react with some of the base part. And the result of that is, as we saw in those equations, we will actually generate some more of the acid part of the buffer. Dramatic drawing here. And we will lower the base part of the buffer in that reaction. Same thing occurs if we added base to it. What we essentially do is the base would react with the acid part of the buffer, and it would make some more of the base part of the buffer. And again, we would use up some of the acid part of the buffer. So it's sort of like I mentioned, it can regenerate itself or part of the buffer as you're reacting with it. And again, you sort of start with good amounts of both of those things. That will allow the buffer to work really well. That is why you don't just add, for example, HF to a solution and go, it's a buffer, because HF is a weak acid, although it will produce some F minus. It is not enough F minus to function correctly as a buffer. That's why you would need to add some additional sodium fluoride to it. And that's why in your experiment, you took a beaker that had something in it, I don't remember, but you had your acetic acid. And if you just put that acetic acid in there, it would generate some acetate, which is the other part of it, but you would not have enough acetate to function correctly as a buffer, which is why you also had to add in some sodium acetate to that buffer to really make it a true buffer. There is a limit to buffers in terms of their capacity. It's sometimes called buffer capacity. And that is because if you either add buffer was too high a molarity, or if you just were not reading the instruction. So let's say I had this buffer. Yeah, as you have the keep adding strong of an acid, at some point it will eat up all of the base part of your buffer, which means once that occurs, it's no longer going to be able to be a buffer. And if you continue to add acid, you're just going to continue adding. At that point, you will see a big jump in pH because you basically blew through your buffer. So sometimes, when you make a buffer, and you'll learn more about sort of making buffers in Chem 1B if you take it, you do need to make sure that the concentration of your actual buffer components do match, sort of the concentration of the acid or base that you may add to it. Any questions on a buffer, how it functions or works? Here's just a little table sort of talks about characteristics of buffer. It is a weak acid and its conjugate base, or a weak base and its conjugate acid. Like I mentioned, you could also do a weak base and its conjugate acid. Buffers, again, resist changes in pH by reacting any added H plus or OH minus, and doesn't let those guys stay free in the solution. Again, that's really what affects it. And those are a couple of the reactions that occur there. Any questions on that? All right, that is chapter 16. Leaves us